Okay, so here's your bell ringer. I'm gonna let you read through that and think through that. It has to do with parabolas, right? And vertex. Trying to help you think through and remember that. And today we're going to talk about quadratics and other polynomials. Your goal is to watch the video or videos from week 13 and then fill out these notes. Use a separate sheet of paper for some examples that we'll do. Although these notes, there are guided notes for that printed for you, and then complete week 13 Delta Math. So complete the Delta Math for the week. So here we go. Ready? Quadratic functions all have an exponent of, you guys know this, I know you know it, 2. That's the highest exponent, and that's the degree of the function. Now, the graphs have a special name. The graphs are called parabolas. The graph of a quadratic function is called a parabola, and it can be written in 3 different ways. One way is called standard form, and standard form really only tells us one helpful thing, or a couple helpful things, but one of which, it looks like this, by the way, ax squared plus bx plus c. And one thing that it tells us is that c is the y-intercept. The other thing it tells us is a little bit about end behavior, right? If a is positive, we know it's facing up. If a is negative, it's facing down, right? So it tells us real quick, whatever a is, it tells us if it's facing up or facing down. Vertex form tells us real quick the vertex. Looks a little something like this. It tells us real quick that the vertex is HK. That's why we like it. And it tells us that it's going to stretch or shrink by a factor of A. It also tells us if it's facing up or down again. If that A is positive, it faces up, negative faces down. And then we have factored or intercept form. And this guy tells us the roots really quick, or the X-Intercepts. It's going to be X minus a number times X minus a number. And whatever those numbers are, let's call them P and Q for now. Whatever those numbers are, it tells us exactly where it crosses or touches the x-axis. So we call those the X-intercepts. If we've got it in some crazy form and we're trying to figure out what the A is, what the A value is, then we use some extra point that they give us, some extra point xy. We plug it in and solve for A. Okay? Okay, so if we are going to write an equation for this parabola, first of all, we know where the vertex is. So that's where we're going to start. We're going to start with vertex form, because that's what it says to use. So y equals some number a, which I don't know what it is yet, times x minus the x of my vertex, so minus 5, squared, plus the y of my vertex. All right, so that'd be cool if we were done, but I got to figure out what this a is right here. So to solve for a, we said to find the a value, plug in one of the extra points on the parabola and solve. So they gave us an extra point. So now I'm going to temporarily plug in y equal to is got to be 20, and x has got to be 7, and then I'm going to solve for a. Okay, well, let's, we're going to start by subtracting 12 from both sides. That's kind of nice and easy. I'll do that. So now I have 8 equals a times, oh, hey, I can do this. 7 minus 5 is 2. And then if I square it, 2 squared is just 4. Right? So then to get a by itself, I'll divide both sides by 4. So a is 2. Ta-da! So my final equation here, go back to all this, except now I know what a is. I'm going to plug that in. A is 2. And then x minus my 5 squared plus 12. Ta-da! That's the answer to that one. Okay. Now, this other example here, it says write an equation for parabolas shown below in vertex form, factored form, and standard form. Okay. So, first of all, is this thing facing up or down? It's facing down. So I know that it's going to be negative, right? Since it's facing down, my A is some negative number. And let's pretend it's just 1 for now. Okay, let's just pretend it's 1 for now. And actually, I think it is because, yep, it is. It goes through, yep, down 1, right 1. So that means it's -1. Okay, anyway, all that said, vertex form, y equals -1, x minus the x of my vertex squared plus the y of my vertex. Okay, well, where's my vertex? My vertex here is at, looks like -2 all the way up at 9, I believe. So -2, 9. So x minus -2, ooh, gotta be careful. Minus a negative really means plus. Remember, let's change the sign. And then, all right, so there's vertex form. Now let's do factored form. Now remember, factored form, we look back what we wrote over here. Factored form is where we look at the x-intercepts. It's x minus the x-intercept and x minus the other x-intercept, or the root. So where does this thing cross or touch the x-axis? Right here, which is at 1, 2, 3, 4, 5, -5, 0. And right here, which is at 1, 0. That's why they call those the zeros, because the y's are zeros. Right? And so for factored form, I know it's negative because it's facing down. And then I have x minus 1 and x minus the other x, right? So I just did that guy. Now I'm going to do this guy. Minus a negative really means plus. And then the last one here, standard form. Standard form might take me a little bit longer, but since I know my vertex form, oh, I don't think I mentioned this. If I start with vertex or factored, to get standard form, all we have to do is multiply it out. Multiply it out or expand it. And that'll give us the standard form. So I have these two. I'm going to multiply. I'm going to pick one of them that I like, whichever one you like better. I don't know. Pick one. I'll pick this one. Okay. I'm going to expand it to get the standard form. All right, well, I'm gonna need a little bit more space then. So let me get rid of that guy for a second. So we're gonna distribute, right? So x times x, don't forget my negative. I'll deal with that in a little bit. X times 5, -1 times x, -1 times 5. Distribute that, combine my like terms, and then distribute that negative. So equals negative times x squared, 5x minus 1x is 4x, minus 5. Distribute that negative. So eventually I get negative x squared minus 4x plus 5. There we go. There's my standard form. Okay, now it says part B. It says, what are the advantages of writing in each of the different forms? Okay, so let's look at just vertex form. What does it tell you real quick? You know, shift left, shift right. shrink or stretch. For factored form, we can easily see the X-intercepts or the roots. Standard form, the only thing that one tells us real quick is that last number there, we call that C, that tells us the Y-intercept. So it was 5 over there, and look, that's where it crosses. C gives the Y-intercept. That's really the only thing that one's good for. Next thing to talk about, completing the square. All right, so the only time we're going to need this is if you were trying to convert from a quadratic from standard form and you're trying to get it into vertex form. Okay, if you're trying to go from standard to vertex form, we're going to have to complete this square. See how there's a squared here? So we're going to figure out what's missing and rearrange some stuff. So the most helpful part of this is actually doing an example. So it tells you step 1, rearrange, then add half of the middle term squared, and then factor and solve. So x squared plus 12x plus, and we're going to leave a space here, blank equals, and we're going to move this 40 over to the other side of the equal sign. And if you move it across an equal sign, you always have to change the sign. Okay? So x squared plus 12x plus blank. Now, the blank, what we're going to do to figure out what that blank is we're going to figure out the half of the middle term and square it. So let me write it off to the side. Half of this middle term, so half of 12, and then whatever we get, square that. Okay, what's half of 12? 6. Square that. 36. So that's what I need in here. But if I put that into equation, I have to put it on both sides of the equation if I add that in. If you add it in on one side, you have to add it in both sides so it's still a balanced equation. Now, the advantage to that is now suddenly I know that this handy dandy deal is the same, and you're going to trust me, is the same as x plus 6 squared. All this. That's why I threw that 36 in there. Okay? That left side is now x plus 6 squared. And then I'm just going to simplify the right-hand side. So negative 40 plus 36. Oh, and if you're like, I don't know how you know that. Okay, let's look at it real quick. 36. What multiplies to get 36 and adds to get 12, right? 6 and 6. So x plus 6 and x plus 6, or x plus 6 squared. Negative 40 plus 36 is negative 4. Now to get this in the right form, now I'm going to move this 4 back over there to get it in vertex form. Okay? So if I move it over, now I got to add it, change the sign. So x plus 6 squared plus 4. And that is going to be what equals y. So that's my vertex form by completing the square. So what this does is real quickly, it tells me my vertex is at negative 6, positive 4. Okay. So again, let's make sure we're on the same page. To complete that square, all right, the x and then anything with an x on one side, anything without an x on the other side. So I moved that negative 40 over. Then I take half of this middle term 12, right? Half of that 12 and square it. Half of it tells me what's going to go in here. Squared tells me what I need to add in to make it work. When you do your delta math, you can see more examples of that. All right, polynomial functions. Dun, dun, dun. They don't have an exponent of 2, but necessarily, but they can only have positive integer powers of x. And that just means no fraction exponents and no negative exponents on the x's. And there's an example there. F of x equals 4x to the fifth plus 3x squared minus 2x plus 1. Any exponent, as long as it's a whole number and it's positive, will work. And so quadratics are a special type of polynomial, right? So we're talking about a whole bunch of polynomials now. X-intercepts, you'll also hear them called sometimes roots. Sometimes you'll hear them called zeros, because it's where they cross, where it touches the x-axis. And that's where the function equals 0, or the y value equals 0. So to figure it out, you plug in the y, or the function equals 0, and solve for x. Now we've talked about this, but it gets a little confusing sometimes, so I'm going to make sure we pull it all together. Y-intercepts, remember, are where the function touches the y-axis. And that's going to happen when x equals 0. So we plug in x equals 0 and solve for y. Okay. Now, when we're looking at these things, we can have a root that can, quote unquote, happen more than once. And when that happens, we call it a multiplicity of a root. And let's say our root was at p, it crossed at some number p. So x minus p to the exponent of some number k means that root p has a multiplicity of k. Okay, that's going to sound ridiculous until we do a couple examples in a minute. And then if that exponent, right, if that exponent right there, that k on a root, if it is an odd exponent on that root, then the function is going to pass through the axis. And what I mean by that, let's say the function does, I don't know, whatever the heck it wants to do at this spot right here, and at this spot right here, that tells you whatever that root is. Let's say this is at 3 and this is at -2. Whatever that root is, because it goes through, it actually passes through the x-axis. It doesn't just touch it and bounce off. Then that tells you it has an odd exponent. So x minus 3 has some odd exponent on it. I don't know what it is, but I know it's odd. And the root of x plus 2 has some odd exponent on it. I don't know what it is, but I know it's odd. If k is even, if that exponent on a root is even, then it's actually going to bounce off the x-axis. For example, let's say this is at -3. And it goes like this, and it just bounces back up. I don't know much else about that function, but I know that x plus 3 has some sort of even exponent on it because it bounces right here. Just bounces right off. Okay. It could be a quadratic, right? It could be where it has it's squared, or it could be to the 4th power, or it could be to the 6th, but some even exponent on there. So let's talk about some examples and see what the heck you can do with this. It says, given the polynomial to the right, which of the following could be the factored form of the function? Okay, well, first of all, let's look at these roots. Where are these roots? Okay. We got -3, -1, and 4. Okay, so I know I'm going to have x, x, and x, right? It touches or bounces 3 different times. And then I'm going to go, okay, so if I look at just this 4 right here, well, x minus 4, that's easy. What kind of well, and then it passes through. It goes all the way through here at 4, so that better have an odd exponent on there. So odd, right? Now let's look at this -1. X minus -1 is really +1. It passes through, so that's going to have an odd exponent. X minus -3, so that's +3, and it passes through, so it's going to be an odd exponent. None of them bounce that time. So I don't care what odd exponent it is, but it better be odd on all three of those. So x plus 3 plus 1 minus 4. Okay, so this one can't be it, right? It doesn't have the right signs. This one cannot be it because it does not have the right signs. And then the other thing we'll need to look at, so, okay, the exponents on all these are odd. This is a 1. Exponent is a 1, 1, 1, 1, 1, 1, right? Those are all just ones. Those are all odd. That works. But, oh, wait, no. One of those is wrong. Oh, I crossed out the wrong one. My bad. Hang on. I make mistakes. I'm human. Okay. Plus 3 plus 1 minus 4. Okay. Plus 3 plus 1 minus 4. So that one does not work. These exponents are odd, but let's see which one will work. So from what we know right now, what we've talked about just now today, let's figure out what happens when we plug in x equals 0, right? So that'll tell us what should happen here at x equals 0. What should happen is the answer should be 2, right? So let's see which one of these gives us 2 when we plug in 0. So if I plug in 0 to this first one, I get 0 plus 3 times 0 plus 1 times 0 minus 4. So plus 3 is just 3, plus 1 is just 1, minus 4 is just -4. 3 times 1 is 3 times -4. That actually gave me -12. That didn't work. Let's try it if we plug it in here. 0 plus 3, 0 plus 1, 0 minus 4. Right, so that gives us -1 over 6 times, we just said all that was 12. And that does equal, or -12, my bad. And that equals 2, which is what we think should happen. It does cross up here at 0, 2. When we plug in 0, the function comes out 2, so that is our answer, according to what we know as of right this second. Now, you and I have talked about it before. Because this buddy on the right goes down and to the right, we know that the front of this thing has to be negative. So between B and D, D was the only one that would work anyway. All right, number 2. Write an equation of a polynomial in factored form with zeros at 3, -2, and 1. Well, if it's factored form, it's going to be pretty quick. Now, I could do a whole bunch of different versions, right? It could be x minus 3, x plus 2, and x minus 1, right? We just subtract each of these guys from x. Or they didn't tell me what kind of zeros these are. So that's a perfectly good answer. Or you could say, I don't know, this could be squared and this could be cubed. They don't tell us the exponents. They didn't say anything about multiplicity. So I can put any exponent on those 3 that I want. Any exponent that you want, you get to pick. But I have to make sure that I've got those guys written in there, right? The factored form of those 3 roots. Okay. Sketch the graph of a polynomial with zeros at -1, 2 with a multiplicity. Oh, this 2 has a multiplicity. That means, and is that an even or an odd number? It's an even, so it's going to bounce. off of that root. So it has a 0 at -1, a 0 at 2, but it's going to bounce, a 0 at 4, and a y-intercept at -5. Ooh, and it's going to bounce at that 2. There's lots of different options as to what you can do with this, but if it's going to bounce at that 2, I'm betting it's going to bounce a little something like this, right? And then go up through there and come up through that. That's my guess. It says it has a multiplicity of 2, that means it bounces. If they don't tell you it has a multiplicity, you assume it's just 1 and it goes through. That is not the only answer, but that is one answer that'll work. All right, last bit of pulling it together notes, and then we'll do a couple examples. This is a lot of information. Polynomial end behavior. Now, we've talked about end behavior a little bit, so this should feel like a review, right? So degree, if the highest exponent on x, exponent, I didn't leave enough space. The highest exponent on x is even. What are even numbers? Like 2, 4, or 6, or 8, etc. Then, and if it's positive, remember the positive, the leading coefficient, the number out front, if it's positive, then on the right end, it's going to go up. So remember, the right goes up. If it's negative, then the right goes down. If it's even, the ends go in the same direction. If it's odd, they go in opposite directions. So let's think about this for a second. Some even thing where the right goes up and they looks like they're going to have to both go up since they go in the same direction and the right goes up. So I don't know what this function is, but it's positive and even, so they both go up. Even degree does not mean even function, just even degree, okay? Even exponents. So if we look at the left side, well, the right side's the easy part, right? As x goes to the right, it's going up because the leading coefficient was positive. So as x goes to positive infinity, the function also goes to positive infinity, right? Now, because it's even, the left side does too. And the way we say the left side is as x approaches negative infinity. Now, if it's even, but negative leading coefficient, then on the right side, it's going down. That right side is going down, but since it's an even degree, the other side's going down as well. So the right side is going down as x approaches positive infinity. The y value goes down. And it's also true on the left. As x approaches negative infinity, the y value goes down to negative infinity. They both go down. Both the x's go down. I'm sorry, both the y's go down, whether you go left or right, because it's even degree, but negative leading coefficient. Okay, now if it's odd, remember that means they're going in opposite directions, but this leading coefficient tells you what's happening on the right side. So on the right side, it's going up. I don't know what else is doing, but on the left side, it's not going up. So on the right side, it's going up. On the left side, it's going down. Another example. Opposite on they're going in opposite directions on the end, but the right side is going down this time. So my right side's going down, and I don't know what it does in between, but the left side is going up. So the right side is going down, and the left side is going up. Whew. That's lots of information right there. Let's actually talk about an example, okay? So describe the end behavior to the right. Okay, now if you're going to tell me in words, what is the left side doing? Let's just do it that way first. The left, whoops, I need to grab my pen, I guess. So the left is going up. So the way we say that is as x approaches the left side, and left side is negative numbers, right? Negative infinity. The function is approaches, it's going up, so positive infinity. Now let's look at the right side. As x goes to the right, this function is going up. So as x goes to positive infinity, this function is still going up, positive infinity. Is it possible for this graph to have a degree of 5? Is it possible for this graph to have a degree of 5? Okay, so degree means exponent, right? Highest exponent. And when I look at this, if it's 5, that would be an odd number. And what's supposed to happen on odd numbers? Odd degree functions. Well, they go in opposite directions on the ends. So is this one going opposite directions on the ends? Oh no, they're both going up. No. Odd degrees have opposite end behaviors. They go in opposite directions. So nope, that won't work. Since both the ends are going up, it cannot be an odd degree. Nope. Which of the following terms, when added to the given polynomial, would change the end behavior? Ooh, end behavior? What changes the end behavior? What changes end behavior? Basically, the only thing that can change end behavior is the highest exponent and the leading coefficient. Okay, so right now this thing has the highest exponent is odd. So it's going in the opposite directions, and the right is going down. So it's odd. So the right is going down, so the left is going up. I don't know what else is happening. Okay. So it says if we add negative x squared. Okay, if we added that, we'd have negative x squared. Sorry, negative 8. I can't talk. Negative x to the 8th power, and then all this, right? Okay, does that change the end behavior? Well, what's the end behavior of this guy? Well, suddenly it's even, and it's negative. So even means it's going on the same direction. It's negative, so it's going down on both ends. Oh yeah, that would change it. That would definitely change it. Oh, it says check all that apply. Oh, this just in. Check some more. There might be more answers. All right, well, let's see. If we put in this negative 3x to the 5th, all right, let's see. We would have negative 2x to the 7th still would be the highest. And we have that 6 would still be there, but then we'd have to pop in this x to the 5th minus 24. Did that change the highest exponent or the leading coefficient? Nope. This is still the same. It's still the highest. So no, does not apply. All right, let's try another one. Which ones do you think will? Which ones do you think will change it? Which ones do you think will change it? The end behavior. this guy. This is the other guy that'll change it because suddenly, if we add 5x to the 7th plus negative 2x to the 7th, we would have 3x to the 7th plus 5x to the 6th minus 24. Now suddenly our exponent is still odd, but this guy's positive. So instead of it going down to the right, it goes up to the right and down to the left. So that would change it. So there's the ones that would change it. There you go. Okay, now that's a lot of information. You have an assignment that's due this Sunday, and we'll talk more in class. Dun, dun, dun.